Okay, we're going to go ahead and get started today. We are going to continue our discussion on chemistry. We're getting closer to the end of that chapter, believe it or not. Lab this afternoon, we're going to start taking a look at bones. We'll be looking at the bones of the skull today. So everything you need for that is found in eLearn in the content for lab. And I'll spend a little time going over the material that you got to look at too. So anyway, we've got almost everybody here. So are there any questions before we start? Okay, then I'm going to go ahead and go into share screen and open up chemistry and see where we stopped. Somewhere in here about chemical reactions. So, okay. I'm going to talk about chemical reactions just a little bit here. I know I probably said this the other day, but it's important to remember these points for a variety of reasons. Okay. Chemical reactions in the body are totally different than chemical reactions anywhere else. Because in a lab setting, you can make a chemical reaction go backwards and forwards all the time. I mean, theoretically, what you start with and what you end up with can be reversed. The reactants become the products, and then the products can become the reactants. Theoretically, if you mix baking soda and vinegar, you're going to have, like I think I used the example of our middle school science fair volcano that a lot of us probably did. You mix baking soda and vinegar together, you're mixing an acid and a base. The acid is the vinegar because it contains acetic acid. The sodium bicarbonate, the baking soda, is the base. And when you mix an acid and a base together, you get a reaction and you end up with a product. Now, in the case of baking soda and vinegar, you get carbon dioxide and water and salt. You started with sodium bicarbonate, you started with acetic acid, that's what's in vinegar. You end up with carbon dioxide, water, and sodium chloride. And in theory, you could reverse that reaction. And reactants and products are large enough that you could probably figure out, there's probably a way to do it. We know that chemical reactions are affected by three things. We know they're affected by temperature. The warmer the temperature, the higher the temperature, the faster a chemical reaction goes. Because the chemical reactions are dependent on the molecules of the reactants mixing together, interacting with each other. Particles of acetic acid encountering particles of sodium bicarbonate randomly moving around. The faster those particles move, the more likely they're going to collide. And when they collide, there is a reaction. Chemical reactions don't occur if the molecules of the reactants don't hit each other, don't collide together. They have to hit each other for the reaction to occur, or have to be in contact, hit each other, be in contact. So if you have baking soda and you have vinegar and you bring them together, you have a reaction. If the vinegar was hot, it would go even faster because the molecules of the acetic acid are going to be moving very, very quickly. If you had the baking soda in solution and it was hot, or at least warmed up, the reaction would go quicker. A higher temperature increases the rate of reaction outside the body. Concentration matters. You increase the concentration of the reactants, you're going to have a faster reaction rate. If some is good, more is better. At least, in a lab setting. The more vinegar you add, the more baking soda you add, the faster your reaction is going to go, the more powerful it's going to be, the reaction is going to be. Reaction rate occurs faster because there's more particles of each to run into each other. If you have a lot of vinegar and a lot of baking soda, you're going to have many, many more particles to interact. If the concentration of the vinegar is greater than if it's like 1% acetic acid versus 10% acetic acid, it's the acid in the vinegar, the acetic acid, that's making the reaction go. There's nothing else in vinegar that would make it go except the acetic acid. If you increase the concentration of the acetic acid, you're going to have a faster reaction. If you increase the concentration of the baking soda, I don't know how baking soda is made, but let's just say that you could go from a 1% to a 10% concentration of baking soda. You get a faster reaction rate. Particle size matters. Only the smaller the particle, the faster the reaction goes, because when these particles are bouncing around and running into each other, smaller particles move faster. So the smaller the particle is, the easier it is to react, because it's going to be moving a lot of them, and they're going to be moving faster than large particles do. In the body, we can't do anything. In the human body, we can't raise the temperature. Temperature is constant, 98.6, 37 degrees Celsius. And we don't change that. The only time we change it is if we have a low-grade fever. And then a low-grade fever is designed to allow our immune system to work more efficiently. And we're talking a 1 or 2 degree increase, but a slight increase allows our immune system to work just a little more efficiently. That's all we can do. And it's only, when we have what we call a low-grade fever. Because low-grade fevers really aren't that as bad as we think. So we can't change the temperature. The concentration in the human body is already extremely low, because we're not dealing with large quantities of any substance, and we can't change that. We can't change the concentration, and the particle sizes are already extraordinarily small. So we're stuck. We can't do anything to increase the rate of reaction based on the properties of the reactants and the products. So we use a catalyst. A catalyst is a compound, usually what we call an enzyme, which is a type of protein. They're called a biological catalyst, and they make the reactions go faster. Even though we can't control the size of the particle or the concentration of the particle or the temperature, but the one thing we can do is use enzymes. We can flood an area with an enzyme that will bring those reactants together. And so it makes chemical reaction. Enzymes make chemical reactions go very fast. They function as what we call a catalyst. And the reaction proceeds at a much faster rate than it would normally, because if we didn't have enzymes functioning as a biological catalyst, then reactions in our bodies would be very slow, because they would wait, they would have to just randomly run into each other for the reaction to occur. So we slide now into the biochemical portion of this chapter. And we're looking at the compounds that affect human anatomy and physiology. The chemicals here are either going to be inorganic chemicals, inorganic molecules, or organic molecules. Now, the division is whether or not there are carbon atoms present. If carbon atoms are present in a molecule, it's going to be considered an organic molecule. The only exceptions to this rule are carbon dioxide and carbon monoxide. They're the only compounds with carbon in them that are not considered organic. They're actually considered inorganic compounds, even though they have carbon. The inorganic compounds include water, all of the salts, usually the acids and the bases, things like acetic acid, sodium bicarbonate, sodium hydroxide, hydrochloric acid, sulfuric acid. These are the acids and bases. Now, we don't encounter sulfuric acid in our bodies, but we do encounter hydrochloric acid and sodium bicarbonate all the time. The organic compounds are the carbohydrates, the sugars that we eat, the carbs, as well as the fats, the proteins, and the nucleic acids. Those are the DNAs and RNAs in our bodies. They are all typically large molecules with lots of carbons, lots of hydrogens, and they're all covalently bonded. Now, of all the compounds in our bodies, the most common inorganic compound is water. Our bodies right now are probably 70% water. As infants are somewhere closer to 80% water. When we deal with elderly patients, they're probably closer to 60% water. The reason that most of our elderly patients have significant wrinkling of their skin is due to a lack of water. Lower water concentrations cause the skin to wrinkle up. Technical term, it shrivels. It's because of there's a lack of what we call turgor. The cells have a lower water concentration. That's why there's skin wrinkles, face and hands and stuff like that. But typically, the average adult is somewhere around 70% water. Water, of course, protects us from rapid changes in temperature. It can absorb a lot of heat. It can release a lot of heat through perspiration. It's the solvent in our bodies that we dissolve everything into. All the salts go into solution in water. The blood cells are carried in salt water. Any solution where there's a chemical reaction taking place is usually done in water. And of course, we use water for cushioning because the fat cells contain a lot of water. Water, as I said, important point, water is the universal solvent, and it carries, in our plasma can carry all the living red cells, white cells, and platelets, as well as all the salts, proteins, hormones, the sugars are all in solution in the plasma. And that's something to think about too with our blood. We say, well, we're talking about like blood sugar levels and things like that. And we're talking about the percent of sugar in our blood. Now, where's that sugar going to be carried? It's going to be in our plasma. It's going to be in our plasma, dissolved in plasma, and it will migrate out of the blood vessel into the interstitial spaces to get into the cell. And this is where insulin comes in. Insulin allows the cell to make openings to channels in the cell membrane to let our sugar go into the cell. But it's transported in the plasma along with all the salts. Now, salts are really important to us. Salts are going to be, they are the ionic compounds. Remember, an ion is an atom that has gained or lost an electron. It's either positively charged or negatively charged. And the salt is any ionic compound that has, as I say, disassociated into its separate ions. What does that mean? It means that, like sodium chloride, salt, table salt, separates into its positive sodium ion and its negative chlorine ion. And the most important of those ions is sodium. Chlorine is just sort of watching off on the sidelines, but sodium is essential to us. Sodium regulates our fluid levels in our body. Sodium affects our blood volume. An absence of sodium can lower our blood pressure. An increase in sodium can raise our blood pressure. I mean, what do if you have a patient with high blood pressure, what are they usually told not to do? They're, among other things, not to eat a lot of salt. So salts are very, very important to us because they help generate, or at least maintain, the electrical charges on our muscle cells and our nerve cells. Now, when an ion is in solution, an ion with sodium ion in solution, for example, it's called an electrolyte. They conduct electrical currents. Remember, we are electrically charged. Our muscle cells have a charge of minus 90 millivolts. Our nerve cells have a charge of minus 70 millivolts. And we have these charges are maintained across the cell membrane thanks to the presence of these charged ions. For example, we have a high concentration of sodium outside the cells. And we have a high concentration of potassium inside the cells. Now, potassium is also a cation. Remember, a cation is a positively charged ion. We'll get into that later on. Now, the most important ions in our bodies: sodium, potassium, calcium, and iron. We don't think of iron too often as an ion, but an iron ion is what we find in the middle of hemoglobin. Hemoglobin is the protein that carries oxygen. The oxygen binds to an iron ion, which is in the middle of the hemoglobin molecule, which is why we have to have iron in our diet to make sure we can make enough hemoglobin to carry enough oxygen. So we have to make sure we have an adequate amount of all of these ions in our bodies. To maintain homeostasis. I haven't said it for a couple of days, so I'll say homeostasis. Balance. It applies to the ions too. The salts that give us the ions are sodium chloride, calcium carbonate for our bones, and for muscle contractions. Potassium chloride. We need the sodium, and we need the potassium. We need the calcium. Chlorine's just watching. Chlorine doesn't get to do a whole lot for us. So the salts are very important here because not only do they function as electrolytes, they function as solute particles, and that's going to drive the movement of water across a cell membrane. And solute particles dictate which way water goes with osmosis. The higher the solute concentration on one side of a membrane, the greater the movement of water towards that solute is going to occur. So if the water concentration is high outside a cell and it's low inside, water's going to go in. Water's low means the solute level's high. So, okay. Sodium chloride disassociates very easily in water. Again, sodium is the most important of all the ions that we encounter. And it's mostly found in the plasma and the interstitial fluid on the outside of the cells. Now, sodium chloride gives us that sodium. Sodium chloride, when it hits water, immediately disassociates into the sodium and the chlorine ions. The water molecules rip apart the salt crystal. The positive end of a water molecule grabs the fluorine. The negative end of a water molecule will grab the sodium. Again, it's like a magnetic attraction. Positive ends of a water molecule grab the negative ends of the sodium chlorine crystal, sodium chloride crystal, and it separates. It goes into solution. It has disassociated. It's still there. The salt doesn't break down. Salt can't break down. Most salt can do is go from sodium chloride into sodium ions and chlorine ions. But water will cause that crystal to break apart into its two components, but it doesn't go away. If you have a beaker of salt water and you let the water evaporate, what's going to be left behind? The salt. You didn't lose the salt because salt and water evaporate. So sodium chloride is easily broken apart. That's why salt goes into solution so easily, because the positive and negative charges on the water molecule are attracted to the positive and negative charges of the salt crystal. It's harder to get sugar to go into solution. If you're going to take, if you dump a tablespoon, or let's make it 100, if you put 100 grams of glucose into a liter of water, it's not going to go into solution easily because the glucose molecule, the sugar molecule, doesn't have a positive and negative end. The water molecule doesn't rip it apart as easily. You have to stir the sugar in the beaker. You have to maybe put the beaker on a hot plate and warm it up to get it to go in the solution. I mean, consider making iced tea. Come back to that example. When you're making sweet tea, when's the best time to add the sugar? After it's been sitting in the fridge, or while the water is still hot. Well, we all know that you put the sugar in while the water is hot. Otherwise, it's going to take a lot of effort to stir up the tea to get the sugar to go into solution. Sugar, a long story to make one simple point. Sugar is not ionic. Sugar has no positive and negative ends. Doesn't go into water as easily. Another part of the inorganic makeup are the acids and the bases. Like acetic acid is an acid. Hydrochloric acid is an acid. We have hydrochloric acid in our stomach to help start breaking down proteins. Hydrochloric acid will dissociate into hydrogen ions and into chlorine ions. The more hydrogen ions that a substance releases when it disassociates, when it breaks apart, the more acidic it is. And so hydrochloric acid can be, based on its concentration, it can be very acidic and be a strong acid because it gives off lots of hydrogen ions. Acetic acid, like we find in vinegar, gives off less hydrogen ions, so it's not a very powerful acid. So, at least in vinegar, you can get vinegar in your hand; it's not going to hurt because the hydrogen ion concentration isn't very strong. So, it's all about this thing being a proton donor. Now, we call hydrogen ions protons because that's essentially what they are. If you take a hydrogen atom and strip away the electron, and now you have the ion, the hydrogen ion. What's left? The proton, and that's all. I mean, think about it. A hydrogen atom has one proton and one electron. One proton, one electron. You strip away the electron. The hydrogen atom now has a positive charge. It's a hydrogen ion. But all that's left after you strip away the electron is the nucleus. And the nucleus has one proton in it. So we say that acids are proton donors because they're giving up their hydrogen ion. The hydrogen ion is nothing but the proton. So no electrons in the hydrogen ions. So we use the term, proton donors, since they're giving up protons. A lot of medications for acid reflux are termed proton pump inhibitors. They act on the glands in our stomach that produce hydrochloric acid. They inhibit the release of the protons, the hydrogen ions. So we, even these medications, we call them PPIs, proton pump inhibitors. Protonics comes to mind as an example of one. Many of your acid reflux medications, I think Prevacid's another one, it's a proton pump inhibitor. They reduce the acid concentration in your stomach by reducing the number of hydrogen ions that are being released. So in our bodies, hydrochloric acid is a very important acid. We find it present in our digestive system. Carbonic acid, H2CO3, that's what gets formed when carbon dioxide and water combine in our plasma. We form carbonic acid, a very, very weak acid. Still a proton donor. That's what acids do. They donate protons. Carbonic acid is a very weak acid, but it's still an acid. Bases are proton acceptors. They grab hydrogen ions out of solution. When sodium hydroxide, which has made up of sodium and a sodium ion and a hydroxyl ion, which is the OH portion of water. Water is HOH or H2O, 2 hydrogens and 1 oxygen. You have the negative portion of a water molecule, which is the oxygen and hydrogen end. When sodium hydroxide disassociates, you get that what we call the hydroxyl ion. The hydroxyl ion accepts a hydrogen ion, a proton. And so when a base goes into solution, it accepts all these hydrogen ions and ends up making water. In our bodies, the two most important hydrogen ion bases are bicarbonate, because we use sodium bicarbonate in our bodies. We make it in our bodies and use it all the time. And ammonia. Ammonia is formed from the breakdown of proteins. And we can measure the concentration of these acids and bases in our bodies using what's known as the pH scale. It's simply a measure of the concentration of hydrogen ions. And the more hydrogen ions you have, the more acid that's present. Now, this is where it sometimes gets a little bit confusing, if I haven't confused you already. The more hydrogen ions you have, the more acidic your solution is. And that means the lower the pH scale reads. So a low pH means high acid. If you're down, pH scale goes from 0 to 14. So if you have an acid that's somewhere around 0, 1, or 2, that's a very strong acid. It's a very powerful acid. It has lots of so a low pH means high acidity. The lower the number, the higher the acidity. A pH of 1 is much greater than something that's a pH of 6. So as the scale goes from down to 0 or 1, like hydrochloric acid in our stomach is somewhere around pH of 1. Carbonic acid in our plasma is probably around a pH of 6 as we move up the scale. Now, the scale is negative logarithmic. I don't think anybody will ever come up to you and say, hey, explain the negative logarithmic scale of the pH system. I have never, ever been asked on the street about the pH scale. And I'll probably never be on Jeopardy and have that as a question if I'm ever on Jeopardy. But a couple of things about the pH scale that we can apply in healthcare. I mean, there is a reason we talk about this. What we can apply to the pH scale is that every time we see a change in the number, if we're going from pH of 6 to pH of 5, an acid that has a pH of 5 is 10 times more acidic than the pH of 6. And if we have an acid with a pH of 4, it's 10 times more acidic than 5 and 100 times more acidic than 6 and 1,000 times more acidic than pH of 7. So with this logarithmic scale, every time we see a change, we have every time we move down the scale or up the scale, it's a 10-fold change. So 6 is 10 times less, I'm sorry, 5 is 10 times greater than 6, 6 is 10 times greater than 7, 1 is 10 times greater than 2, and 100 times greater than 3, and 1,000 times greater than 4, and 10,000 times greater than 5, and 100,000 times greater than 6, and 1,000,000 times greater than 7. So the scale, as we move up and down the scale, we see a change, a 10-fold change. So like it says here, a solution of pH 5 is 10 times more acidic than a pH of 6. Our bodies don't like to fluctuate with the pH. We like to stay, believe it or not, slightly basic, right around 7.35. That's actually a pretty precise value there for us, right around 7.35. If we start moving upward, we don't like it. If we start moving downward, we don't like it. 7.35 is actually a little bit basic, because 7 is neutral. Anything above 7 is basic, moving into the hydrogen, the proton acceptor stage. Our bodies are very, very rigid in what's acceptable on the pH scale. So when you're getting blood work results in your patient, a pH value is something that you pay attention to. If your patient is if the pH if their pH range, if their pH is very low, their blood is very acidic. And the question is why? So we go, if it's acidic, it's anything from 0 to 6.99. 7 is neutral. Distilled water is neutral. If we go anything from 7.01 to 14 is basic. The high with a base, the higher the number, the more basic it is. With acids, the lower the number, the more acidic they are. So hydrofluoric acid is going to be somewhere around pH of 1, but sodium hydroxide is going to be somewhere around 14. Oven cleaner, for example, is going to be close to that. Here's our scale. Give you a good example of this. Neutral, pH of 7. Our blood is around 7.4, 7.35 to 7.4. If it's set at 7.4, if we get above 7.45, we're getting too basic. If we get below 7.35, we're getting too acidic. Coffee has a pH of 5. Wine has a pH of 2.5. Stomach acids are around pH of 2, and hydrofluoric acid is between 0 and 1. Up here, ammonia is about 11. Oven cleaner is around 13. Sodium hydroxide is around 14. Egg whites are slightly basic, pH of 8. So a lot of things that we encounter are going to have a pH here. Now, what do we pay attention to in the body? We pay attention to carbonic acid and hydrofluoric acid, bicarbonate ions and stuff like that. We want to make sure our blood and our plasma stay right around 7.4 to 7.4, between 7.35 and 7.45. That's our safe range. We get above that or below that, we start having complications. We don't like that. So why do we have all these acids and bases here? Well, we use acids in our stomach to break apart proteins, and we use carbonic acid as a way to carry carbon dioxide back to the lungs. A lot of the carbon dioxide forms carbonic acid, so it can be carried in the plasma to the lungs, and then we can release the CO2 from the carbonic acid. A lot of times we use acids and bases to neutralize each other So if we get too acidic, we can neutralize that acid. If we produce too much carbonic acid, we can neutralize it with a bicarbonate solution. When you mix acids and bases together, just like your baking soda and vinegar solution, sodium bicarbonate, baking soda is the base, acetic acid, vinegar is the acid. You mix it together, you get a neutralization reaction where you end up with the release of carbon dioxide and production of water, and you form a salt, sodium chloride. We call these we use neutralization reactions with something called buffers. We don't want to see a big swing in the pH of our body. We don't want to be shooting up to the above 7.45 or shooting below 7.35. So we use buffers, and we can use the buffers to neutralize excessive acids in our plasma or excessive bases. Okay, so that's pretty much the basic chemistry from the inorganic side here. Let's talk about the organic side. This is the much more interesting side. Organic molecules all contain carbon. They all contain carbon. Carbon dioxide and carbon monoxide are going to be the exceptions. We don't count those as organic compounds, even though they have carbon, but they're still, so only molecules containing carbon that are covalently bonded to other carbon atoms make the cut as an organic molecule. Carbon is neutral. It has usually picks up. It fills up all of its covalent. It fills up its covalent shell with hydrogen atoms covalently bonded to. So sharing those electrons, and carbon is happy. It's also bound to other carbon atoms. So as long as it's sharing its electrons, everything is fine. It is a neutral. It is considered a neutral atom because it binds so easily with hydrogens and carbons. And oxygen binds very easily with them. And it shares the electrons. It never loses the electrons. It never gains electrons. So carbon is pretty special because no other atom does that. No other atom will bind to 4 other atoms and never give up its electrons, and after it does. Now, the organic compounds, all based on carbon, are going to be the carbohydrates, the lipids, the proteins, and the nucleic acids like the DNAs and the RNAs. Organic compounds are what we call polymers. They are long chains of carbons and hydrogens and oxygens linked together. So they very large molecules. They're built from small molecules. A large molecule is what we call a polymer, meaning many little molecules linked together. And the term here is a monomer. So the carbohydrates, why do we pay attention to the carbs? Well, those are all the starches and sugars that we deal with. We don't make starch, we don't store starch. We're not a plant. So we can't go outside and photosynthesize. But we still produce a starch-like product. So all the carbohydrates contain carbon and hydrogen and oxygen. They show up in a 1 to 2 to 1 ratio. 1 carbon to 2 hydrogens to 1 oxygen. Carbohydrates are what we use for fuel in our bodies. The simplest carbohydrate we deal with is something called glucose. It's what we call a simple sugar. If you drink a Coke, you're drinking a version of glucose called fructose. It's a variation simply in its structure. So it's called fructose. It's a 6-carbon sugar. Glucose is a 6-carbon sugar. Fructose is a 6-carbon sugar. So galactose is a 6-carbon sugar. There's very little difference in these sugars other than they are made of 6 carbons. They have 6 carbons, 12 hydrogens, and 6 oxygens. And we use these simple sugars as fuel. Glucose is our main energy source. It's our only energy source. Everything we do is based around glucose. If we don't get enough glucose in our diet from carbohydrates, we start breaking down fats and proteins and converting them to glucose. The term for that is gluconeogenesis. Genesis means creation. Neo means new. So neogenesis is new creation. Gluconeogenesis is the creation of new glucose. And our bodies can take protein, can take fat, and chemically break them down and convert them into glucose when we don't have enough glucose of our own. Now, if you're a carbohydrate, you come in 3 categories. You are either a monosaccharide, which is a simple sugar. A monosaccharide would have 6 carbons, 12 hydrogens, and 6 oxygens. Glucose, fructose, are monosaccharides. The simple sugars are the monomers of the carbohydrates. A disaccharide, di means 2, so we have a double sugar here. A disaccharide consists of 2 monomers. Glucose and fructose together form table sugar, what we call sucrose. Sucrose is stuff that's in the white packets, that you go to Weigel's and get coffee and you want sugar for your coffee, and you have the white packets of granulated sugar. That's sucrose. That's, again, what we call table sugar. So stuff that when you go down to Food City and you buy a 5-pound bag of sugar, that's what you're getting is sucrose, 100% sucrose. It's made up of 2 simple sugars. The one that we use all the time, glucose, and fructose, the sugar that we find in corn syrup. So glucose and fructose make sucrose. So these are the disaccharides. We don't use them for fuel. We have to break them down into glucose. So if you're eating that Snickers bar is made of glucose, made of sucrose, and you have to break it down into glucose to get energy out of it. Now, the polysaccharides are the many sugars linked together. They are made up of lots and lots and lots of monosaccharides. For example, starch, like you find in a potato, baked potato or fries or tater tots or anything like that, mashed potatoes, however you like your potatoes, if you like potatoes. Potatoes are full of starch. That's stored energy from the plant. Those potatoes are plants. Well, the starch in a potato is nothing but hundreds and hundreds and hundreds, probably thousands and thousands of glucose molecules linked together. That's what starch is. So it's a very large molecule. It's a great storage medium because it has lots of stored energy. Consider the stored energy in a molecule of glucose. One molecule of glucose linked, 100,000 times gives you starch. Think of all the energy in a potato or an apple or anything starchy like that. Now, we don't store excess energy as starch in our bodies. But we use a polysaccharide known as glycogen. We store that in our liver. We don't store starch. So this is what a glucose molecule or any 6-carbon sugar molecule looks like. It has 6 carbon atoms arrayed in a ring. It has 12 hydrogen atoms, those little silver balls there, and it has 6 oxygens. Those are the red ones. So 6 carbons, those are the black balls. Those are the black atoms there. The red atoms are oxygen, and the silver atoms are the hydrogens. But they are, you can see that they are arrayed in a ring. So these simple sugars usually have 6. Some have 5 carbons, but usually 6. We link these sugars together, these simple sugars together, to give us our disaccharides and our polysaccharides. Now, if we have a 5-carbon sugar, that usually only shows up in our DNA and our RNA. These are what we call the pentose, or 5-sided sugar. Ribose and deoxyribose. So the pentose sugars are pretty much DNA and RNA. The 6-carbon sugars show up in glucose, which is our blood sugar, fructose, which we find in corn, as I said, in corn syrup, and in lactose. So these are the big, most important of the monosaccharides. The pentose sugars, ribose, deoxyribose. And remember, the name DNA is deoxyribose nucleic acid, and RNA is ribonucleic acid for the 5-carbon sugar. And the 6-carbon sugars, glucose, fructose, and galactose. This is what they look like. Their structures are very, very similar. They're a ring structure. They all have 6 carbons in some type of ring. And we see, fructose is a little unusual. The ring has 5 sides. You have 1, 2, 3, 4. You have 4 carbons in the ring, and then a carbon that sticks up on this end, another carbon that's attached in this end. So it still has 6 carbons, and it's still a ring structure. It's still a 6-carbon sugar. Here's glucose with 5 carbons in the ring, and then a 6th carbon sticking up here. Galactose, very similar structure to glucose, just it has to do with positioning. You'll notice all of them have an oxygen bound into the ring. So not that matters or anything. These are the 3 common monosaccharides. The disaccharides are the double sugars. Now, one advantage of the disaccharides is they have lots and lots of energy, stored energy, potential energy. But the downside is that they're big. They're too big to get across the cell membrane. Cells can't get the disaccharides inside because it's a huge molecule. Cells can easily get glucose to come in. We use insulin. That's what insulin does. Insulin stimulates the cells when our blood sugar levels rise. Insulin gets released to stimulate the cells to make channels and carriers, openings through the cell membrane to allow glucose to come in. And so they build these special, what we call carrier proteins or channel proteins, essentially openings or passageways just for glucose to go into the cell. That's what insulin does. But sucrose, the double sugars, are too big. They're twice as big as glucose. Glucose has a molecular weight of 180. It's a large molecule. But sucrose, a double sugar, has at least 300, has a molecular weight of at least 360. It's a bigger, much bigger molecule. It can't get through. Sucrose, maltose, which is malt sugar, lactose, which is milk sugar, the stuff that we say people, when people are diagnosed as lactose intolerant, meaning they can't process lactose. These are the larger sugars. We have to break sucrose, for example, or lactose or maltose down to convert it to glucose. So glucose and fructose, give you sucrose. So sucrose, when it's broken down, well, when you break it down, you'll break it down and form glucose and fructose, and then convert the fructose to glucose, because we want glucose. So we store all of our energy we take in. Okay. So these are the disaccharides. Simply two monosaccharides linked together. This is table sugar. This is, again, what you put in your coffee to sweeten it up. So, and there's nothing wrong with sugar. There's nothing wrong with any food, I think, as long as you eat it in moderation. Do you like, if you love peanut butter sandwiches, I'll just use that as an example. How many peanut butter sandwiches do you eat on a daily basis? If you like fried chicken, if you like seafood, how often do you eat it? How often do you eat burgers or barbecue? We're getting in dangerous territory here, because most of us like barbecue in some form or another. Do you eat it every day? It depends. Lots of people like biscuits and gravy. Lots of people eat biscuits and gravy every day. Is that moderation or not? It depends. It depends on what your body's doing. Anyway, so there's nothing inherently wrong with sugar. Just how much are you using? Same applies to anything we eat. Okay, so these are the three big disaccharides. Sucrose is the number one. You're gonna get packets of table sugar sucrose anywhere you go. Any place like Weigel's or Pilot, or where you're gonna get coffee or tea or whatever. Generally not gonna get packets of lactose or packets of maltose, for your coffee. But lactose is what shows up in dairy products. Maltose shows up in malt. Maltose is what shows up in alcoholic beverages that you may enjoy that are brewed. So, depending on the type of alcohol that you prefer, if you prefer any alcohol, it shows up in there. The last category are the polysaccharides. These are the very large molecules. This is what shows up. These are the carbohydrates that show up in our cereals and in our breads and in our pastas. These are the large starchy foods. Things like baked potatoes, spaghetti, French fries, biscuits, rolls, bread, all the things we probably like to eat. Polysaccharides are very long chains of monosaccharides linked together, usually glucose. Thousands and thousands and thousands of glucose molecules linked together, one after another, after another, after another, giving you lots of stored energy and making a very large molecule. Plants form their polysaccharides into starch. Plants make glucose. Plants make, when a plant photosynthesizes, it takes energy from the sun and carbon dioxide and water and makes glucose. And it stores it as, it combines that glucose with other glucose molecules, makes starch, and stores the starch in the leaf or in the fruit, like in the case of an apple, or in in the root, like a potato. And so this is the plant's stored energy. That's what plants do. Now we eat plants. We can eat the fruit. We eat an apple. The apple, the pulp of the apple is starchy. It's a healthy food. A potato is a healthy food. It's like, how do you find an unhealthy food? Well, you got to do things to it. You got to kind of modify it, for example. We'll get to that in a second here. But plants store their starches in the leaf or in their fruit or their tuber, if you will. It's like sweet potatoes, carrots, potatoes themselves, in their seed pods, like corn, like beans and peas, in kernels like corn. That's all filled with starch. That's where the plant is putting its stored energy. So we don't store polysaccharide. We do not store starch as our polysaccharide. We can store polysaccharides in our bodies. We can store energy and park it. We park it as glycogen. It's a polysaccharide made of long chains of glucose molecules linked together. But glycogen is what we store in our liver and in our muscles. It is what we use to draw on when, if, for example, your blood sugar level drops, you didn't eat breakfast today, you were in such a hurry to get to the computer that you forgot to eat. It might happen. Anyway, you didn't eat. Your blood sugar level, it starts dropping below the normal level. Your body says, hey, you're probably hungry and your blood sugar is low, and it will release a hormone from the pancreas, not insulin, but something called glucagon. It's the antagonist. It's the opposite of insulin. Glucagon acts on your liver to say, hey, release some of that stored glycogen and convert it to glucose, simple sugar. And it does, we do, and it does, and it raises our blood sugar back up to where it's supposed to be. So we don't store starch, but we store glycogen. So whatever our cells can't take in, we end up storing to use later. Not a bad deal. Same principle, it's the same principle as a potato plant, storing energy in the tuber, or a plant storing starch in its leaf, for example. That's what they do. Now, the polysaccharides are not soluble in our diet. We can't process polysaccharides. We have to break them down into the starches. And a lot of these polysaccharides are not soluble, are not digestible at all. For example, cellulose. Cellulose is a polysaccharide version of starch in plants that form the walls around the cells. Now, what does that mean? Well, if you've ever eaten corn, canned corn, cream corn, corn on the cob, any kind of corn, you may have noticed a day or two later that the corn kernels have passed through your body and have remained intact. The kernel, the outer covering of the corn kernel, you've eaten the contents. The contents of the kernel is where the juicy, starchy material is that we can process. But the cellulose layer that gives the kernel its yellow appearance or its white appearance or its mixed appearance, doesn't matter. That's undigestible. It passes on through as fiber. So if you eat a couple layers of corn, you get all the good stuff out of the corn, but the kernel covering itself will show up in your feces later because it's not digestible. Same thing with salads. If you like to eat spinach salad or romaine lettuce. That's all cellulose. Cellulose in its leafy structure. You get the contents of that, but you don't process out the cellulose. High fiber foods are high in cellulose, the indigestible polysaccharide. And if you have even more cellulose in a plant with something called lignin, then you've got wood. Wood burns. That's like a real revelation. Wood burns because it's high in energy, stored energy. That stored energy is derived from polysaccharides. And again, when you're burning wood, and you are breaking covalent bonds, releasing heat and light energy and electrons while that wood is being destroyed. You're releasing the stored energy in a log. Okay, I'm supposed to be talking about foods. Okay. Starch and glycogen look pretty much the same. They're both chains of long molecules of glucose linked together. They branch a lot, so they don't look that much different. Cellulose is nothing more than all these glucose molecules linked together, but in a straight line, linked both horizontally and vertically. And so that forms a fiber, which is much harder for us. We have a very hard time trying to process these fibers. We usually can't process these fibers. This is what cellulose looks like. It's in all the plants. It's in the walls of the plant cells. It's in wood and in bushes. I mean, this is why you can't go out and pick up a handful of grass and start eating it. You're not going to get it to break down into anything. So this is the carbohydrates. Now, what do we eat from the carbs? We eat the starches. We can break down the starches from plants. We can break that down easily because wheat flour, wheat is made into flour. We grind up the wheat kernels and we eat the stored starch. If we have whole wheat, it's because we didn't take the bran. A wheat kernel has an outer covering of cellulose. And that's, if we don't want that kernel there, it's removed and we get white bread. If we want whole wheat bread, then we include the kernel, the bran kernel on the outside, and it's ground up, and we eat that, and we have more fiber in our diet. Now, so we eat anything made of anything made of starches, pastas, and bagels and donuts. Anything with made with flour, going to contain carbohydrates. All that is carbohydrate. Eat potatoes, carbohydrates. Carrots, carbohydrates. Apples, carbohydrates. Fruits, carbohydrates. Just because it's a fruit doesn't mean that it can't be eaten in excess, because it's still containing carbohydrates. So, second category are the lipids, the fats. And we always look badly at fats, but fats are healthy too. We have to have a certain amount of fat in our diet. It comes down, it all comes down to how much are you eating of the carbs, the lipids, the proteins. So the fats, the lipids, have the same atoms in there, carbons, hydrogens, and oxygens. It's a slightly different arrangement. Sometimes the fats will throw in phosphorus. I'll show you that in a minute here. Fats are not soluble in water. You think of oil and vinegar. You mix oil and vinegar together, and what happens? The oil settles out on top of the vinegar because the vinegar is mostly water. It's acetic acid and water together. That's vinegar. And the oil, whatever kind of oil it is, you know, olive oil, corn oil, it doesn't matter, is not going to go into solution in the water. It's insoluble. The fat molecules do not play well with water, and so they will float on top of the water. So all fats are insoluble in water. You can't take oil and mix it up in a beaker of water and have it go into solution. It will not do that. Now, if you are a fat, you come in 4 categories. The neutral fats, the triglycerides, term you may have heard, triglycerides. The neutral fats or triglycerides are the most common type of fat, of lipid. When I say fat, I mean lipid. So, the phospholipids are what shows up in our cell membranes. It gives our cells their water-hating qualities, because our cells do not like water to come in. In fact, if we have to have special channels just for glucose, for sugar, we have to have other special channels just for water. It's the only way we can get water into the cells. So we have the triglycerides, we have the phospholipids, we have the steroids. The steroids are all based off of cholesterol. Cholesterol is a steroid molecule. Steroids all have a 4 or 5 ring structure. They're all very, very similar in appearance. The only difference is the molecular groups that are attached to the end of the rings. These steroids include things like estrogen, progesterone, two female sex hormones, testosterone, male sex hormone, and of course cholesterol itself. All these steroids are derived from cholesterol. They all are very, very similar in appearance. Their actions are different, but their appearance is very, very similar. Then we have a 4th category called the icosanoids. These are fats that are found locally that have roles to play, usually in anti-inflammatory processes to fight inflammation in our bodies. Okay, the triglycerides. When we say fat, we're talking about a solid fat like butter or animal fat or lard. That's a fat. A lipid is called an oil when it's liquid. A lipid is called a fat when it's solid and an oil when it's a liquid. So if you take a bottle of canola oil and you have a block of butter next to it, they're both lipids. One is a fat and one is an oil. Chemical structure is pretty much the same as far as the makeup of the carbons and hydrogens and oxygens. It just, their shape is different. They have different shapes. They have different appearances and shape. One's a solid, one's a liquid. So a fat is a solid lipid and an oil is a liquid lipid. So that passed, liquid lipids. So all of our triglycerides have the same chemical makeup though. They all consist of a glycerol atom, a 3-carbon alcohol. And little organic chemistry here, very little organic chemistry, but anytime you have a molecule that's its name ends in OL, like glycerol, then it is an alcohol. Or ethanol, it's an alcohol. So anytime we see the OL ending, it's an alcohol. In this case, glycerol is a 3-carbon alcohol. It's 3 carbons in a row with the alcohol structure on the end. Well, you have the glycerol alcohol, and then attached to that are 3 long chains of what we call fatty acid molecules. There's a special molecule fragment that makes things acids, and that's attached to each of these fatty chains, these long chains of fats, of these long chains of carbons and hydrogens. So we have these 3 chains of fatty acids. That's what glycerol is. So I mean that's what a triglyceride is. The name sort of gives it away. Triglyceride. Tri for 3 fatty acid chains, and attached to glycerol, the alcohol glycerol, triglyceride. What do we use triglycerides for? Well, we always think, well, they're evil, or evil chemicals, or evil molecules. Well, we store energy there. We insulate our bodies with them, and we protect fragile organs that don't have any other protection, like the organs of the abdomen, like the kidneys, for example. No protection from bones or anything like that. So this is what a triglyceride looks like. Over here on the left-hand side is the 3-carbon glycerol. Carbon, carbon, carbon in a row. And this group, this OH group here and here and here are indicative of an alcohol. That's called the hydroxyl. That OL ending again, hydroxyl. So this is an alcohol over here. This is glycerol. It is bound to 3 fatty acid chains. This group here, every time you see this carbon and a double bond to oxygen and another OH, another hydroxyl group, that's what we call the acid group. You need to worry about that now. But that's what makes this an acid. So we have 3 fatty acid chains. The chain is nothing but a whole bunch of carbons and hydrogens linked together covalently. Because look, carbon and hydrogen, carbon and hydrogen, carbon and hydrogen, carbon and hydrogen, and so on. 20 or 30 of these linked together. And they're all containing carbons and hydrogens. Lots of potential energy there because we have lots of covalent bonds with lots of electrons in the valence shells of the hydrogens and the carbons. So we have 3 of these together, and that, when they're combined, that gives us the neutral fat, the triglyceride over here on the far right. The glycerol linked to the 3 fatty acid chains. This is a triglyceride or neutral fat. Now, if you are a triglyceride, you can either be saturated or unsaturated. If you are a saturated fat, and you've heard that term, I'm sure, it's on all food packaging. If you look at, if you have a cereal bar, a fruit bar, a candy bar, a bag of chips, anything, even on the back of your Coke bottle, it'll have the food ingredient label in there. It'll say, fats, saturated fats, mono, unsaturated, polyunsaturated, and so on. A saturated fat means that it has the maximum number of hydrogens bound to the carbons that it can possibly have. So it means all the carbon atoms in the fatty acid chain are linked together with single covalent bonds. And that means that when you have single covalent bonds, that means you have the maximum amount of hydrogen atoms that can be attached to that carbon atom. So you end up with, you saturated it with hydrogens, essentially. Lipids, triglycerides that are solid at room temperature are saturated fats. All the animal fats, you have a piece of meat and you trim the fat off of it, lard, animal shortening, if you will, and butter, and animal fat. They're all solid at room temperature thanks to the saturated fatty acids. I mean that all the carbon atoms are linked together with the maximum number of spaces available for hydrogen atoms to be linked to the carbons. looks like this. This is up here in the top is a saturated fatty acid. Carbon, 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 and so on. There are hydrogens available to bind to every carbon. So every one of these carbons here has 2 hydrogens until we get to the end. It has 3 hydrogens. So it is the maximum number here. That's a saturated fatty acid. Now, the opposite of this is the unsaturated fatty acid. Remember I said saturated fats are solid at room temperature. And the reason they're solid at room temperature is thanks to van der Waals attraction. Van der Waals attraction between the 3 fatty, let me go back here a couple of slides. Right there. This is a fatty acid chain. If it's fully saturated, van der Waals attraction between these chains, that very minute shift in electrons temporarily will cause the chains to be attracted to each other almost magnetically, and they'll stick together. And it happens over and over and over again, so that the fatty acids, the triglyceride is solid. As solid as butter can be, as solid as animal fat can be, or as solid as lard can be. But it's not a liquid, thanks to this van der Waals attraction, because these chains are so close together and they're attracted to each other and they form a solid. And so that's what's happening up here. The opposite of this is the unsaturated fatty acid. An unsaturated fatty acid has a double bond somewhere in the chain. Instead of having, like we have here, carbon linked to a hydrogen here, and a carbon in front of it, and a carbon behind it, a saturated fat has a carbon linked to another carbon with a double bond. Instead of sharing two electrons, they're sharing 4 electrons, which means that there's no room for a hydrogen here and a hydrogen here, because all the bond spaces are filled up. The double bond causes the fatty acid chain to bend, to kink at that double bond position. It bends out of the way. Not only that, but it also pivots around the double bond. And now, since it has become kinked and bent and pivoting, you're not going to get van der Waals attraction between the other chains, because this chain, like this chain here, is not going to allow itself to get close enough to this chain for van der Waals to work, because we've got a double bond here. We're missing 2 hydrogens, but all the spaces are filled up. But we still have 2 less hydrogens, and that double bond allows the fatty acid chain to bend and twist and rotate. And this is what we would say an unsaturated fat has a double bond in here. So this summarizes everything I've been saying. Fatty acids can be up to 20 carbon atoms long. They may be saturated, they may be unsaturated. If it's saturated, there are no double bonds. The maximum number of hydrogen atoms possible are held there. If it's unsaturated, it has 1 double bond. If the fatty acid is polyunsaturated, and these are terms we've heard of in food, a polyunsaturated fatty acid has 2 or more double bonds. I think I got a picture again. So here we see, this is a saturated fatty acid right here. This is palmitic acid. These saturated fatty acids show up in the solid fats, animal fat, for example, lard, butter, things like that. The unsaturated fat over here, oleic acid, has the bend. There's the double bond right there. And the unsaturated fatty acids tend to all be plant fats. Animal fats are solid at room temperature because they're saturated and they have van der Waals attraction. Unsaturated fats are liquid at room temperature. They have double bonds and they have no van der Waals attraction because of the bending and twisting and kinking of the fatty acid chains. The plant oils, the olive oils, the corn oils, the safflower, sunflower oils, all of these plant oils are going to be unsaturated at room temperature. They're going to be liquid at room temperature because they're unsaturated. Okay, and that's all. I don't have enough time to go into this, so I'm going to stop us here at lipids. And anybody have any questions about this? Next time you go down to Food City to buy a bottle of cooking oil, read the label. You'd be surprised what's on there. So I drive my wife crazy because I'm like, well, look at this one. This one's got 3 grams of unsaturated fat, and this one only has 2. And she said, well, just pick one. So anyway, so we're moving right along here. We're going to maybe wrap all this up next Tuesday. We'll see. So again, lab today, if you're in the afternoon lab, we're going to be looking at the bones of the skull. And I'll talk a little bit about getting ready for the bone test in a month or so. So otherwise, I want to get us out of here. Thanks for coming. I'll see you next week.